Hey, what's going on? In an effort to try and move ahead with thermal energy and being in the middle of Winter Carnival, I decided that I would make a video of the notes of how to calculate thermal energy. So the quality's not very good because we're doing this quick and on the fly, but I'm hoping it'll work just fine. So first off, the amount of thermal energy a substance has, like gold or cement or water, depends on a few things. And you should have learned this in your simulation, that the amount of thermal energy a substance has depends upon how many particles you have, which we measure as mass, which we measure in grams or kilograms. Typically in our lab we'll be using grams. The second thing that is dependent on thermal energy is how quickly those particles are moving, something that we measure as temperature. We'll typically use degrees Celsius, but don't be surprised if you see Kelvin used. We won't use Fahrenheit very much at all. So we have mass, we have temperature, and what your simulation taught you is not everything heats up at the same rate. Gold, silver, sodium, copper, metals, they tend to heat up very rapidly. Compared to glass, wood, foam, plastic, they tend to heat up, they require a whole lot more energy before they get hot. And that property, how reluctant something is to heat up, is known as specific heat. So how much thermal energy an object has depends upon the object's mass, how much you have, the temperature, how quickly those particles are moving, and lastly, the specific heat of the material. Now, specific heat is specific to your material. So whenever I give you a problem that's asking you to calculate the amount of thermal energy, I will have to give you the specific heat. I'll give you an example. The specific heat of water . 4.18, and the units here would be joules of energy. It takes 4.18 joules of energy to be absorbed to raise 1 gram of water by 1 degree Celsius. If you don't want to write specific heat over and over and over again, we use lowercase c. So you could say the C of water, of H2O, is 4.18 joules per gram degrees Celsius. So, if I know these things, I can figure out the amount of thermal energy in an object. So, that's what you need. You need to know its mass, you need to know its temperature, and you need to know its specific heat. So that's what we'll do now. So this is a mathematical calculation. We know that when we put the hot flask, or the flask containing hot water, inside our cold beaker, that my flask lost energy, my beaker gained energy. Well, here we're going to actually calculate the exact number of joules that are either gained or lost. So we have the change in thermal energy. If it is a positive change, and what that means is your substance absorbed thermal energy, or it increased in heat. If it's a negative value, a negative change, then that would mean that your substance lost thermal energy. The formula for this looks pretty intimidating, but it's not. It's a piece of cake. So long as you remember that the amount of thermal energy a substance has, there's a typo here by the way, the amount of thermal energy a substance has depends on mass, temperature, and specific heat. So long as you know that, you have that in your head, then the formula is easy. Here's the formula. Q equals MC delta, this is Greek letter delta, looks like a triangle, T. Q equals MC delta T. So let's break it down. M, as we said on the previous slide, is the mass of your objects. Most likely in this class will be in grams. C will be given to you. That's the specific heat of your material. And the units for specific heat are joules per gram degrees Celsius, or typically the units we'll use. And lastly, delta T refers to your change in temperature. Whenever you see this delta, you want to read that as change in. To get a change, we always take the, we always subtract the final temperature from the initial temperature. And you might remember this from when we did acceleration, way back at the beginning of the course. Remember, acceleration was equal to your final velocity minus your initial velocity over time. Way back then, I could have taught that as delta V over T, final minus initial. Here, we have mass, specific heat, change in temperature. If my change in temperature is positive, I absorbed thermal energy. If my change in temperature is negative, I lost thermal energy. So Q, this mysterious Q, is my amount of thermal energy that I either gained or lost. So it's my change in thermal energy. So from the simulation you did, the virtual lab that you did, we have an example. In that virtual lab, you were giving a bunch of substances. So let's say that you have your 5-gram block of wood. So in this simulation, your 5-gram block of wood was heated. So I have a 5-gram block of wood is heated from, and in that online simulation, it started at 20.0 degrees Celsius, and I think it ended at 37. Everyone had that same final temperature, the 37 degrees Celsius, okay? I need to tell you the specific heat of a block of wood. And that's been calculated by scientists. So the specific heat of wood is less than water. Water was 4.18. Wood is only 1.76, and my units are joules per gram degree Celsius. So I have a 5-kilogram block of wood. It's heated from 20 degrees Celsius to 37 degrees Celsius. The specific heat of wood is 1.76 joules per gram degree Celsius. I need to calculate, or I want you to calculate, the change in thermal energy. Pause this video if you need to. Try it yourself. I'm going to work through the solution here. Before we do, take a step back and look at how complicated this sounds. A 5-kilogram block of wood is heated from 20 degrees Celsius to 37 degrees Celsius. The specific heat of the wood is 1.76 joules per gram degree Celsius. Calculate the change in thermal energy. It seems cumbersome. Go back a page. I know that my change in thermal energy is equal to my mass times my specific heat of my material times my change in temperature. So let's do it. We're going to plug that equation right here. Q equals mc delta T. On my left-hand side, I'm going to make a list of all my variables. Q, which I don't know. M, C, initial temperature, final temperature, and I'm going to add here change in temperature, which you get from subtracting initial and final, right? Final minus initial. So, if you look at the problem, you tell me, what is the mass of sample that was given to you in this problem? What other information was given to me in this problem? I went from 20 degrees up to 37. So my initial was 20 degrees Celsius. My final was 37 degrees Celsius. If I subtract 20 from 37, I end up with a positive number. I end up with 17 degrees Celsius. That means that my block of wood absorbed enough energy, that its temperature rose 17 degrees. This is a positive change, and that's what I want in this situation. So great. So I have that. Boom, boom, boom. I don't know the specific heat of wood. That's not a number I just carry around in my brain. But my problem tells me the specific heat of wood is right here. 1.76 joules per gram degree Celsius. So, plug it in. I've done all the hard work. The rest, piece of cake. What's my mass? Boom, 5 grams. What's my specific heat of wood? 1.76 joules per gram degrees Celsius. What's my delta T? I already calculated it. It's 17 degrees Celsius. Before I go further, check it out. Grams in the numerator, grams in the denominator. Boom, boom. Celsius in the denominator, Celsius in the numerator. Boom, boom, they cancel. I'm left with joules, which is a pretty good thing because I'm asked to figure out the change in thermal energy, which is measured in joules. So I know I'm getting my problem right. I've set it up right. I know that my change in thermal energy would be equal to 5 times 1.76 times 17. And if you do the math, I'll give you a second. Seconds up, you should end up with 149.6 joules. If this sounds vaguely familiar to you, the simulation that you used, the virtual lab that you used, when you added the heat from the Bunsen burner flame, every single time you used 150 joules. So that simulation was based on the specific heat of wood. Exactly. So we're going to use that information. We'll do one more problem. I'm going to have you do this one. So let's say we take a 10-gram sample of copper. And I'm using your simulation data, a 10-gram sample of copper started at 20 degrees. It was heated to 59 degrees Celsius. The specific heat of copper you think it's more or less than wood? Is it more or less than water? We're talking about copper, metal. Is it easy to heat up? If it's easy to heat up, it has a low specific heat. Specific heat of copper is 0.39 joules per gram degrees Celsius. It only takes 0.39 joules of energy to change 1 gram of copper by 1 degree, where it takes 4.18 joules to change 1 gram of water, 1 degree Celsius. So go ahead, solve the problem. Pause the video, solve the problem. You got about 152.1 joules. You're right on. Good work. Now you know how to calculate thermal energy, so now we're ready to look at the heat diffusion of ice, and that's up next.